Usually about a continuous progression of time. Plants grow taller with time, clothes are drier, get drier, lighter and drier with time. Seems natural, but there are other ways to think of change. Another way to think of it, of change, is in repetitive cycles. Days are cycles, seasons are cycles, sound vibrations are cycles. So this can be an intuitive way to think about some phenomenon. We're going to call the first way of thinking sort of linear time as thinking in the time domain, and second as thinking in the frequency domain. So we all know how to describe functions in the time domain. It's just an ordered pair. You have on the x-axis you have time, and on the y-axis you have some sort of value. How do you describe in the function domain, in the Fourier, the frequency domain? Well, you break apart the function into smaller or other little elements, so periodic elements, other functions, which when you add them together, they reconstruct the original time domain function. And this functional decomposition is called the Fourier transform. And so the Fourier transform just takes your original function and it breaks it down into a sum of wave-shaped elemental functions called sinusoids. And each sinusoid can be described with three parameters: frequency, amplitude, and phase. So let's kind of scroll down and see what we talk about. So frequency corresponds to how many sinusoids peaks appear per unit time. And so you increase the frequency, the peaks become more frequent. Amplitude corresponds to the height of the peaks, so you increase the amplitude. And phase corresponds to how the peaks are shifted. Notice how when I shift the sinusoid, you kind of get the same sinusoid when you shift it again. So you start here. If I shift it a bit more, you get the same thing again. It's a bit like going around in a circle. And in fact, phase is often referred to as an angle, phase angle. When you add together these sinusoid components, you get a closer and closer approximation of the original function. When you add them all together, you get a perfect reconstruction. So we're going to show you what I mean here. So here's the original ones. This is the ECG signal. And I'll show you what happens when you add more of these components. You're going to do a run through it. Yeah.
Yeah, I'm going to do that.
Okay. Okay. So here's with one component, and as I add more components, the sum of all the components so far produces a closer and closer approximation of what's above here. And when you increase a bunch of components, like here's 111, you can see that looks pretty close. What happens if we go to 250? Even closer, and so you get more and more detail as you increase the number of sinusoid components.
So the blue line is what's to be added next?
That's correct.
So now at this point, it's like you're barely adding anything.
Essentially, and so that's a good point. So what this kind of implies is that you can get most of your information with a relatively small number of components, and this is kind of used as a basis of data compression for audio and video type signals.
We kind of did like the same type of concept when we talked about principal component analysis. We were like throwing out dimensions.
It is a sort of dimensionality reduction. That's true.
Yeah.
Okay, so sampling. How do you take real world continuously with varying information and bring it into the digital domain? You take measurements regular intervals. And we call these regular measurements samples in the process of taking the measurements sampling. How frequently the samples are collected is referred to as the sample rate. And we refer to a function that conveys information as a signal. So it's a signal. We're talking about a function that conveys information. And standard signals include sound recordings, stock prices, temperature readings, radio transmissions. We sample a continuous signal at a high enough rate, the original signal can be reconstructed perfectly. So to take this one, for example, I take these points, regularly take measurements, and you can see how you kind of draw a curve or kind of connect the dots, and you can reconstruct it, more or less. But what happens if we continue to increase the frequency of the signal, but not the sample rate? So I'll show you what I mean. So I'm increasing the frequency of the signal I'm measuring. So it goes up, and so far it's looking pretty close. And then we're at half, and it's completely gone off. And you increase it more, it's looking even worse, you know. But as you can see, I'm increasing the frequency of the input sample, but the reconstructed signals going down in frequency. And I increase it again, and it goes in reverse. It kind of reflects downward. So anyway, what's happening is, in essence, you can only reconstruct a signal when the highest frequency in it is less than half the sample rate. And this is a result of the Shannon-Nyquist sampling theorem. And the highest frequency that can be sampled is referred to as the Nyquist frequency. And you can see here, let's see. So as you add frequency components to the original signal beyond the Nyquist frequency, they get shifted downward as you go up in frequency. And when they get to zero, as you continue to increase, they go back up again. And this sort of shifting is called aliasing. And it means you can't tell whether a frequency was there or not, because it's corrupted by these reflected other components. I'm sure some of you gamers have heard anti-aliasing. Anti-aliasing is the process in visual signals of removing frequencies that are too high to be displayed on your display. They're filtered out by the anti-aliasing process to produce a smoother result. All right, so the Fourier transform allows us to break up sampled signals into sinusoid functions, which construct the original signal. We talked about that. Let's see here. So when you perform the fast Fourier transform on an array of data, you get an array of equal size containing the parameters of the sinusoid components. Each array element specifies a sinusoid completely, and the elements are often called bins or frequency components. The index of the bin determines the frequency as a fraction of the Nyquist frequency, and the contents of the bin specify the phase and the amplitude of that component. And you can take this transformed array and go back to your original signal by doing the inverse fast Fourier transform. And it takes all those sinusoids and add them together again. So how do we specify phase and amplitude in a single bin? There's supposed to be two different measurements. And the answer is complex numbers. Complex numbers are a type of number with the sum of two components, a real number and an imaginary number. And they're represented like this. A and B are real numbers. And so you have A plus BI, and I is called the imaginary unit. It's defined as the square root of -1. Square root of -1 makes no sense. You can't count anything like that, but don't worry about it. We don't really care. It's just about, we're really interested in the properties, the mathematical properties of these numbers, not any kind of intuition about them. let's see. So you can, what happens, you can add them, it's pretty normal. You could just say that, they're commutes. You have all the algebraic properties of real numbers. You can add them together. And you can multiply them. And when you multiply two imaginary numbers, you get a real number because I squared, and I squared is -1. So you get negative AB. And if you take increasing powers of I, you multiply I times I times I over and over again, you get the same values over and over again. So you get I to the first power is I squared is -1, cubed, -I, 4, 1, and then 5I. This will continue over and over again. And this is sort of the essence of the reason why complex numbers are useful for describing repetitive periodic phenomena. So there's a geometric interpretation of complex numbers that is quite useful to think about. And so you can think of them like a vector in which the x component is the real part, which is A in this case, and where the y component is the imaginary part, which is B here. And when you think about it this way, the angle, you can think about this vector, this as a vector like this. So you can increase the length of it and the angle of it. And these both correspond to different real and imaginary parts. So I can make it bigger, and that corresponds to a real part of 19 and an imaginary part of 32, and a argument. Well, let me go back for a second. So just like vectors have magnitude, so do complex numbers. Complex numbers have a magnitude, and it's called the absolute value of the modulus. It's defined the same way as a magnitude in a vector. It's just the length of it. And so, just like how in a vector, the magnitude of a vector is the sum of the squares of the x and y component, the square root of that. Well, the length or modulus or absolute value of a complex number is the same thing. And you think of the angle with respect to the real axis here, or the x-axis, think of it as a vector, is called the argument. And it's a type of arctangent. It's not the normal one that you use. It's called atangent, but you can think of it like an arctangent.
In any case, it's just that angle of it.
Yeah, it's just the angle versus with respect to the x-axis.
Yeah.
Another way you can think about complex numbers is the scaling factors for a sum of elemental sinusoids. So those two elements in this case are sine 2 pi ft and cosine 2 pi ft. And if you scale these by the two components of this complex number, you can achieve any you can create any sinusoid by simply adjusting the really imaginary part of a complex number. So I can do this and that, and if you adjust it just right, the two components, the sum, which is the black one, where'd it go? Yeah, the black plot is the sum of the two components. And so you can adjust the real part or the imaginary part and get whatever sinusoid you want. And so what this means is that for a given frequency, the complex number can specify the phase and the amplitude. And a common operation is called conjugation. And it's just you take the negative, you negate the imaginary part of the complex number. And what this does is it just negates the phase. And so if it has an angle of 45 degrees, it'll have an angle of negative 45 degrees, and we take the conjugate. So plotting FFT. The first bin is often called the DC component, and it has a frequency of 0 and it represents a constant offset. And then the first half of the bins that follow correspond to normal positive frequencies. As the index increases, the frequency increases. And the second half of the bins correspond to the negative frequency components. Now, negative frequencies don't make a lot of sense when you think about them, but they're really a consequence of the fact that the FFT is done in complex numbers. So when you're doing the FFT, are you asking a question?
Oh, you can do that.
When you're doing the FFT with real valued signals, so the input has real values, the transformed positive and negative frequencies are just the complex conjugates of each other. So there's like no new information of negative frequencies. So as long as you treat the positive and negative frequencies the same when you're doing your analysis, or when you're doing your processing, when you do the inverse transform, like things will come out properly. But you gotta make sure you treat them both the same. So you multiply one by 5, you're gonna multiply the other by 5, or else you'll get strange results when you do the inverse transform. Here's just a plot of that. You can see like these first half here are the normal, the positive frequencies, and then these on the right are the negative frequencies. Okay. But yeah, you can see how they're just copies of each other, right? Like in this magnitude plot, and it's hard to see in the phase plot, but you'll take my word for it that when you look at this number, this value here, on the other side, it's going to be negative, so it's going to be down there. So the phase plot should be interpreted with care because the phase of 0, or the argument of 0, is not defined. And when you have really noisy data, if it's a small value, any fluctuations in the data can cause crazy fluctuations in the phase because it's such a small amount. Like it just takes such a small amount to push the vector in the opposite direction and completely change the phase. So you gotta be careful with that, with like noisy but weak signals. Okay, so when we plot the FFT from now on, we're only going to plot the positive frequencies. So the bin with the highest frequency corresponds to the Nyquist frequency, and we will assign this frequency to be 0.5, and the frequency of the DC bin to be 0. And the frequencies in between are going to be equally spaced with respect to their indices. And these frequencies are called normalized frequencies, and they allow you to talk about the frequency domain generically. So if you want to get to what the real frequencies would be, you just multiply the normalized frequencies by your sample rate, and that'll give you the real frequencies, or the actual frequencies. So a lot of the tools you use in the software is going to be in terms of normalized frequencies, and you just have to convert them to the actual frequencies as part of your code or whatever. Okay, yeah, so this is just the first half kind of blown up. You can see better detail. So the FFT assumes the signal is perfectly periodic, so it repeats itself over and over again forever. So one way to imagine to think about this is that the samples are stored in a circular list. So the ones at the beginning and at the end are right next to each other. But this is not the way things are in reality. And so the result you get from this mismatch of expectation and reality is edge artifacts. And so let's see. So here's our signal right now, and then here's it repeated 3 times. You can see here that these edges, where they didn't quite align, there's that jump there.
Because like when you look at the first one, right, it's the disconnect between the very first point on the graph and then the very last one.
Exactly.
They're not at the same level.
No.
If it were periodic, then they would meet exactly at the same.
Exactly. So you get this jump here, which is unnatural. And what that manifests is blurring of the peaks when you plot them. And the solution to this is windowing. Windowing multiplies the signal by a windowing function, which attenuates the samples at the edges to make the jump less prominent. Popular window function is the Hamming window, but there are many other windowing functions, each with different trade-offs. Rectangular function is more accurate for comparing frequencies, and the Hamming is more useful for comparing the amplitudes of peaks. But yeah, here's the Hamming window. You can see that it reaches a maximum in the middle, and at the edges it falls off.
Hamming, is that connected to the L1 norm?
It is connected to the R-coded Hamming of great fame in computer science. So yeah, it's the same Hamming.
Heading distance.
Yes, that
Hamming cycle.
He was quite prolific in his day.
Okay.
And he was also a big proponent of frequency domain analysis. If you've read some of his other books, he's written several books on numerical analysis and visual filters. Okay, so you can see what's kind of flattened out the edges. And you can see repeated 3 times this jump is a lot smaller now. And you can see that the peaks here, there's a deeper valley between the two separating them. So let's see if I can scroll through and show you guys a bit better. It's kind of subtle here, but they are a little bit easier to resolve. It's more apparent with a more busy signal, but I was trying to make it easier for people to comprehend here. Okay, so plotting about the time frequency domain. Many times you want to know the frequencies that make the signal at a point in time. So like if you're determining the pitch of musical notes in a song, you have to measure each note in isolation. So how do we do this? The obvious way is to calculate the FFT for sequential segments of the original signal and analyze the frequency components of each segment. So you take the input signal and break it into overlapping subarrays, perform the FFT on each subarray, and analyze them. So I'll show you what that looks like. So here's our plot with a sudden frequency change. It starts out, kind of low, and then it's so high you can't really even see the fluctuations. So it's just from just relatively low frequency to really, really high. And the way this looks on the spectrogram or the time frequency plot is like this. And so the vertical axis is normalized frequency, and the horizontal axis is time. And so this allows you to see the frequency components at a given time. Let's see what happens when we increase the length of the segment of the subarrays. Let's make it really big. You can see that the edges are kind of feathered off and subtle and indistinct. You can't really tell where the jump happens, but the accuracy at which you can determine the frequencies is better. The height of this little line here is narrower. We can really pinpoint what that frequency is. It gets even worse when you make the segments longer. Yeah, look at that. It's really tight, but man, I have no idea where it starts and ends. Meanwhile, if you go back to a really low value,
It's the frequency equivalent of anything.
essentially, yeah. If you get really low, then yeah, it's really obvious where it changes, but the frequency precision is pretty poor. So there's a fundamental trade-off between frequency precision and time precision when you're measuring both at once. The Heisenberg uncertainty principle states essentially that you can't know both position and momentum of a particle with perfect accuracy at once. The more accurately you know position, the less accurately you know momentum, and vice versa. So let's examine a photon. The position of a photon is x, we'll describe it here as x. C is the speed of light, and t is time. The momentum of a photon, p, is equal to Planck's constant times frequency over the speed of light. We just showed there's a trade-off between measuring time and frequency. Well, position is a function of time, and momentum is a function of frequency. The Heisenberg uncertainty principle is not something inherent to quantum mechanics, but rather it is due to a fundamental limitation of the measurement. So FFT allows convolution to be performed at high speed. Convolution is an extremely useful operation with a wide variety of applications, including smoothing data, filtering out any desired frequencies, and aligning signals. Convolution in discrete or sample domain is defined like this. You can kind of think of this as like the two of kind of sliding the two arrays against each other, multiplying their corresponding elements, and then adding it all together. And I'll show you what I kind of mean by that a little further down. But it's kind of a sliding and adding operation. You slide one function against the other, multiply their corresponding elements, and then add it all up. Now, why do we want to do this? One use for convolution is for smoothing data to remove noise and reveal larger trends. When smoothing the array the array that characterizes the smoothing is often called a kernel or a filter. A particularly well-known kernel is in the following form. So between 0 and w, it's 1 over w. Otherwise, it's 0. So it looks kind of like a square, like this right here. Yeah, see that black square right there. This is called the boxcar rectangular kernel. With the boxcar kernel, we are adding together neighboring samples within a window and dividing the sum by the length of the kernel. This operation is also known as the moving average. So convolving the signal with a boxcar kernel results in the moving average of the signal. Notice that the sum here is infinite. So we only have arrays of finite length. So one way to do convolution on finite length arrays is to assume that each finite array is a segment of an infinitely long array and concern ourselves only with the portion of the convolution where the sliding segment overlaps the stationary one. So only where the kind of cross over each other. So we'll just kind of play around with this convolution here. So K changes the width of the kernel, so we can make if we make the kernel wider, when you take a moving average of a longer period of time, things get smoother, so that makes sense. So we're using a wider kernel. V is the length. And so we can change the length of the signal array, which we're trying to filter here. And we can change the frequency of the information in the signal. And so what's going on here is me show you what I mean when we're doing convolution. So let's say the kernel is right here. Okay? So the green value right here is equal to the product of the black function with the blue function added all together. So you multiply all these points together and then add them up. And that gives you the green function. So it's kind of this kind of multiply add operation. Well, the naive way of doing convolutions requires a lot of work. So you ship the sliding array one element and then multiply every element in the two arrays together and then add them up. And you do this for each sample in the stationary array. This corresponds to big O of n squared time complexity for convolution of arrays of the same length. But we can do better than that. There's an interesting property of multiplication in the time domain versus the frequency domain. When you multiply two signals in the frequency domain, this corresponds to convolution in the time domain. So that means when we perform the FFT on two signals, multiply them together, and then perform the inverse FFT on the product, the resulting signal is the convolution of the two input signals. The FFT is the time complexity of big O n log n. So for large signals, the FFT approaches can be much faster. And this kind of flourishing F represents the Fourier transform, and the 1 to the negative 1 is the inverse. So, but there's a catch. Because the FFT assumes the signal is periodic, the FFT approach doesn't perform ordinary convolution, it performs circular convolution. And in circular convolution, we act as if the samples are one big circular array, such that the first and last samples are actually right next to each other. Okay, so here's our moving average kernel, and then here's our smooth signal. You can see that we smooth, and then we kind of loop around and drag some of the smooth values over here. As you can see, like here, up here, when we reach the end, we just kind of like petered out, as we kind of got further along on the on the x-axis, but here when we get past the length of the signal in question, kind of go back around to the beginning again. And so one way you can deal with this is you can pad the end of the arrays with zeros, and this will give you something that looks like what we have above. You can also just discard this as well.
You can also pad the beginning of your other data.
That's true as well. You can pad the beginning as well.
Or use it.
You don't use a handing window for this because it distorts the data. So another way to use convolution is to filter out undesirable frequencies. So it's useful for producing music or tuning radios or compressing data or things like that. And a simple way to remove undesired frequencies from the signal would be to set the respective bins in the FFT transformation to 0 and then performing the inverse FFT. So this would correspond to multiplying the transformed signal by a step function in the frequency domain and then inverse transforming. I'll show you what I mean. So you have the FFT of this signal, and then we kind of multiply it by a step function here. So we multiply it by this, and then it's 1 up to here, and then 0 after. So everything after this frequency is discarded. Multiplication in the frequency domain corresponds to convolution in the time domain. So there should be a function which, in transforming the FFT, yields a step function in the frequency domain. And this function is called the sync function, and it has this definition. It says sine pi t over pi t. And frequency cutoff filter can be made from the sync function by scaling it by the cutoff frequency. So here's the filter, the sync filter kernel times 2f sync TN. What does this look like? So we can try experimenting with the filter below. So you can adjust the cutoff of the filter. You see it kind of makes these ripples wider on the sync, and you can see that it shifts the step to a lower frequency. So that does what we would expect. Notice that there's these peaks here and there. That's undesirable. It's called ringing, and it gets worse when you have fewer points. So endpoints is the length of of this filter kernel in samples. You can see that there's this bump, there's a big bump there. That's no good. And the reason for that is because of this edge effect, right? This doesn't line up with that. So you get, you get artifacts. And so what you can do is apply a window to this, this function, this array here, to make the ends match up with each other. So we'll enable window. And then there you go. Look at that. Look how neat that is. It's like a perfect little cutoff. And so you can tweak it however you want to for your application. And this just removes frequencies above a certain threshold. But you can actually keep frequencies above a certain threshold by simply this is called a low pass filter, so it retains these low frequencies. So you can keep frequencies above a certain threshold by simply taking the low pass filter, so you're retaining the low frequencies, and then subtracting that from the original signal. So you're basically subtracting the low frequencies that you kept from the original signal, and this just leaves behind the high frequencies. So that's how you can, if you're interested in the high frequencies, you just
subtract off the low pass filters.
Yeah, you subtract off the low pass filter data, and you get the high pass filter. Does that make any sense? I'm not sure if that's very clear.
What applications would you be interested in high pass?
In a high pass filter? So one example would be, say you're making music, right? And a speaker can't pass frequencies below a certain level. A speaker's not going to be able to pass sounds at 1 hertz. And so you could burn up the speaker like that, passing current at those low frequencies at high amplitudes. So you filter that out so you can only pass the frequencies that the speaker can transmit.
Likewise, in Dolby signals where you have different channels for your high frequency speakers, you call your tweeters. You filter out all the low pass stuff, whereas the subwoofers you filter out on high pass.
Right. You can also there's also what's called band pass, which is you just kind of combine low pass and high pass together, and you keep some frequencies in the middle. So you can do that too. Or you can do a notch filter, which is the opposite. You keep the low and you keep the high, but you cut out stuff in the middle. And so you can kind of combine these together to get whatever you're looking for.
And the fun part is the equalizers. They effectively provide you with inputs in order to adjust the weights on the frequencies you're going to retain. And that's how, the old-fashioned slide in and line out.
So this would be the same algorithm used on equalizers?
It would. Yeah, modern digital equalizers use the FFT. And an equalizer is basically what we call a filter bank. When you describe it like that. Okay, so it's often useful to determine where two signals best align with each other. And one way to do this is by cross-correlation. And cross-correlation is like convolution, except the sliding array is reversed first. And the frequency domain, reversing the signal corresponds to taking the complex conjugate of each element. So the cross-correlation looks like this. So you have the F function, which is, you take the complex conjugate of the transformed F multiplied by the transformed G, and then you take the inverse. So here's an example of why you want to do that. In sonar, something called the ping is sent out by a speaker, and a microphone listens for echoes reflecting off of objects. Distance to the objects is determined by how long it takes for the echo to arrive. How do you decide what a ping should sound like? Well, you could use clicking sounds like dolphins. When plotted, a click looks like a spike, like that. And reflections look like a series of spikes, like that. For good resolution, you want the spike to be narrow, and for a loud echo, you want the spike to have a lot of energy. And so these spikes are narrow, they have good resolution, and these spikes here have a lot of energy, but they're wide, so they have poor resolution. Energy is just the area under the curve. So yeah, for a narrow speak to have a lot of energy, it has to be very tall, but a tall spike requires a lot of power. Greater power means you need more powerful electronics and speakers to generate the click sound. The power of a signal is the square of the amplitude, and the energy is the sum of the power. So the energy is the sum of the square of power, or the square of amplitude.
Do you mind if I had a real example of that?
Sure, go ahead.
I work for Halliburton. We would basically process subsurface findings, various strata and fault lines. We would do it as we set up a microphone array.
Could you raise your voice a little bit, just so we can hear?
Oh, sure.
Thank you.
I used to work for Halliburton, and we would process, what's called underground visualization. And we would set up a microphone array, and then we'd set off a string of explosive charges and listen for reflections of the differences in the rock density, and use the timing from when we knew the charge was exploded to when we received the reflections in order to find the strata. Now, much of the same way that all of these things can be comprised of various other sounds, what we do as soon as we identify the first reflections back from the first change in rock density, we'd subtract that off. We'd run through the process again to find the next rock density change. And using items that we could verify, like core sample drillings, we could eventually map the time that sound could go through different densities of rock, and then come up with a relatively accurate estimate of how far down each different strata of rock was.
Yeah, the FFT is used for that kind of processing. It requires some assumptions as to the shape of the waveform for you to get good results. I don't really know a lot about
And
it.
it requires some assumptions as to the shape of the transition of the rock too, because like faults, we had to have completely different processing for those.
Yeah, it's very involved. So, right, so for a click to have a lot of energy, it has to be wider, but this limits the resolution. So in the frequency domain, the narrower the spike, the wider the bandwidth. So good resolution implies wide bandwidth. I'll show you what I mean. So for I'll show you by wide click and narrow click. So this is the narrow click, and these are the wide clicks. So they have the same power, but since the area under the yellow one is greater, it has more energy. And you can see how this plot here. Let's see. And then the power spectrum. This is a little bit hard to interpret, but
Power is it? Power is it?
No, the two graphs above are the cumulative area between the x-axis and the curve.
that's
So
right.
it's not really the power is the amplitude, the power is the accumulated area underneath the
Right.
curve.
So
So like
this-
at
this-
zero, there's almost no curve on yellow. And, you can see this graph, as in the middle, there's like no area underneath the curve, so it's not increasing
This
anymore. But
this
then-
graph is the integral of the one above, starting at zero.
But it's like an absolute value, because it's only the area between.
So it's a little bit hard to interpret, but what I'm trying to show you here is that this wide the narrow click has energy over a wider range of frequencies than the wide click. So what that means is wider bandwidth. Is more energy over a wider range of frequencies means wide bandwidth. So it seems like a trade-off here. For a given chirp loudness or energy, you can have low resolution and low power, or high resolution. Can have, yes, that's right. Low resolution and low power, or high resolution and high power. Can we do better? Bats use chirping sounds, but the pitch is too high for us to hear. Maybe we should try that. Chirp looks like a winded sinusoid which increases in frequency when plotted. So we start with low frequencies. It goes up and up and up, but it also goes down in amplitude. So kind of like has this kind of, it looks like that. And you can see here's what chirp reflections look like. So these correspond to the exact same reflections as these do here, right? But with the chirp sound. But you can see like the chirps, they overlap each other. You can't really see anything. Like they just kind of like get all squished together. You can't tell where it started and where one ended. So they're hard to discriminate. But the chirping has a lot of energy relative to the power it requires. So you can see the power of, here's the narrow click, here's the chirp. So they both have the same, actually this is narrow click's a little bit louder, or a little press, a little more power. But if you look at the areas, the energy, the chirp has way more energy than the narrow click. It also has more bandwidth than the wide click. So the wide click we said has poor resolution, but poor bandwidth because of poor bandwidth. Well, the chirp has kind of wide bandwidth. So maybe you can get good resolution with it as well. We can. Using cross correlation. With cross correlation, you slide the chirp across the reflected signal and see where they match. And so you take that chirp waveform, kind of advance it along, multiply and add them together, and and then kind of collect that data. And you can see here's what it looks like in cross correlate. You can see those reflections just fine in the cross correlated data because you're seeing how well the reflection matches what you sent out. And because you know what you sent out, it makes it easy to kind of pick the signal out from the noise. Sometimes you want to know when a signal repeats itself. And one way to do this is by doing autocorrelation. And it's the same way as cross-correlation, except that you're cross-correlating something with itself. And one way this would be useful is determining heart rate from ECG measurements. So here's some ECG measurements. And here's our autocorrelated ECG measurements. And so what happens is we take this entire signal and just kind of imagine shifting it over and multiplying and adding it together. And when you shift it over one heartbeat, you're going to get a big spike. When you shift it over two heartbeats, you're going to get, because that's where they line up with each other. So let's kind of filter this out. We're only interested in the first peak because that's going to correspond to the period of a heartbeat, for the whole signal. So that'd be this one here. And so what we can do is we can filter out all these other peaks because they correspond to heartbeat rates that are not humanly possible. And so the lowest heart rate is 26 beats per minute, world record, and the highest is 480. So if I remove all of the heartbeat periods, so like if you take a heart rate, like beats per minute, if you do the reciprocal, you could do minutes per beat, right? So that there's an inverse relationship between period and frequency. And basically what this tells you here is This is seconds per beat is what these essentially represent. And so what we can do is we can filter, we can kind of trim out the range of humanly impossible, heartbeat periods. And so we are left with this sort of slice of data here. And then all we have to do now is just find the tallest peak. And that's pretty easy to do. And that's this one right here. And the resulting calculated heart rate is 127 beats per minute. And so we were able to calculate that quite easily using the FFT. And it's pretty difficult to actually take two adjacent peaks in noisy data like this because you can't tell exactly how tall they're going to be. You can't tell. Look at this, it's kind of like, see these little spikes, like it can be quite difficult to just do peak picking on noisy data, but it's really easy on this nice smooth autocorrelated data. So it can be quite useful for this application. But if anybody has any questions, I'm happy to try my best to answer them. Sure.
Are you familiar with, what's his name, the mathematician who won the Nobel Prize back in the 30s? Edward, I pulled it up, but I forgot his name. Albert Michelson?
The Michelson interferometer?
Yeah.
Yeah.
Do you know that he built a Fourier analyzer that could do both transforms and analysis out of mechanical gears? It's actually quite fascinating.
Mechanical gears?
Yes.
Yeah.
This math, because all of this math is based off of sinusoids. And one of the ways that you would represent a sinusoid in mechanics is you would literally just have a gear that rotates. Okay, and then you've got your angle, and then the gearing ratio can provide you with your amplitude and a few other things. There's a really fascinating set of YouTube videos that I watched a few years ago that talk about his machine. And in some ways, like one of the things is you talked about transforms, but you didn't talk about analysis in a way that was very easy to see. Analysis is when you start off with a bunch of sinusoids and you build up an arbitrary wave. Okay? Transform is when you've got an arbitrary wave, you're trying to do the opposite. You're trying to subtract off the sinusoids until you get the same sinusoids that would be used to build that arbitrary wave. If you take a look at the device on YouTube, there's a very short, like 3 or 4 minute video. I think it would drive home from a visual point of view a lot of the basics of the math that you're talking about. Of course, you've got a lot of good stuff in here on like how to actually use it. But if you wanted to, you can look it up.
Sure.
And I think the magic words to Google for YouTube is introducing a 100-year-old mechanical computer.
Introducing
A 100-year-old. We eventually sold like around 6 of them, and UIUC has one of them. So that first video is just the introduction, and the introduction is enough. If you watch them all, it'll be like about 4 hours of content, but that first video is only about 3 minutes, and you can see it operate, and we'll just kind of talk about it.
Sure. This one here?
Yeah.
Before electronic computers, people built mechanical computers to perform specific mathematical operations. One such machine was this, Albert Michelson's harmonic analyzer. This 19th century machine adds together cosines to create intricate patterns. Amazingly, it also does the inverse operation. It can take a pattern and reveal the cosines that when added together will approximate it. This operation is called Fourier analysis, and is possibly the most important mathematical technique of the past 100 years. Without Fourier analysis, there would be no MP3s, JPEGs, or cell phones as we know them today. To celebrate this stunning machine, and to gain a greater insight into what Fourier analysis is and how it works, I'll share in this video some history of this analyzer, and then in 3 additional videos detail its operation. In synthesis, I go step by step and examine the key components of the machine and how each plays its part in adding cosines. In analysis, I show you how the machine uses the same mechanical motions to find the frequency components of a signal you want to analyze. And in operation, I show the steps an operator of this machine must go through to perform these calculations. This machine's designer, Albert Michelson, was famous for measuring the speed of light, yet he also measured many other properties of the universe precisely, like the diameter of stars or the rigidity of the Earth. In the late 19th century, he performed Fourier analysis by hand to help resolve fine details of the light emitted by vaporized elements. He was doing an early version of Fourier transform spectroscopy. These hand calculations were laborious, so he invented this machine to automate these calculations. He built a prototype machine similar to this one in 1897, and then a larger prototype 4 times the size a year later. The machine was then commercialized by William Gardner and Company. They made precision scientific instruments often designed by Michelson. In their 1904 catalog, they advertised this machine, which can add up to 20 different sinusoids, as well as a larger version that calculated with 80 sinusoids. We know that in the early 20th century, Gardner sold at least 4 of these machines, and based on that, it seems this 20-element machine sold for around $225, and that it was likely made between 1901 and 1910. After this period, the machines are mentioned only occasionally. We found pictures of several different configurations until it made one last public appearance in an improved form at the 1933 World's Fair in the Great Hall of Science in an exhibit called The Magic of Analysis. Our machine has an unknown history. We're not sure when it arrived here on the University of Illinois campus. We only know that for at least the last 40 years, it is set in a glass case in Altgeld Hall, its gears completely still. Join me as I bring back to life this stunning mechanical computer. I'm Bill Hammack, the engineer guy. Watch the other videos in this series.
Let's not watch all the other
Analysis.
videos in the series, but, you know,
To learn more about
the mathematics and the
companies
concepts
that-
go back a long time. And, you know, it's so fundamental. It really is a great way of looking at items, especially items that have any kind of periodicity to them, or, you know, items that are just difficult to analyze. Frequency domain is not particularly easy to understand because it's sort of like, it literally is 1 over the time domain. So, you know, but it's very useful.
So you just going to digital case law.
But did you
I was
know?
planning on doing a follow-up on digital filters where I include something like that.
Yeah.
But
Did you know about the machine?
I did not. I knew about one that Lord Kelvin did. This was called the harmonic analyzer, and it seems like a similar concept.
Okay.
But I haven't heard this one in particular.
Cool. Thank you very much.
Does anybody have any questions? Or?
Yeah, so how can we use that to find oil?
Get some ladies, get a pickaxe.
You start off with the first very safe operation of obtaining a small quantity of explosives.
A very safe operation.
What's that?
For autocorrelation,
Mm-hmm.
it's
Fortunately, lithium doesn't come in huge pools.
For autocorrelation? No, it's for
Or
autocorrelation.
maybe
It's in
fortunately,
logging
considering that when you exposed it to air.
Yeah.
because all of the sliding is done at once to be multiplied in the Fourier way. So you, excuse me.
that was interesting. Made this.
You know, when you did the autocorrelation, you take the Fourier transform of the signal, and then you multiply it by the complex conjugate of that same transformed signal, multiply them together, and then you do the inverse transform, and that gives you the autocorrelation. And the complexity of that is that, so the Fourier transform is n log n,
And then you just multiply.
and you multiply together, that's complexity of n. And so the overall complexity is n log n, and so that's how you get n log n autocorrelation.
Maybe you've seen it, Pro, over off of Main. Yeah. Yeah. What they do is, they use slightly different mathematics, but it's still kind of rooted in Fourier transform, where they effectively create waves, the length of days, hours, weeks, months, years, and they look for trends in airline pricing. And those trends are then used in order to combine with a different model that is kind of a scarcity model.